in Middle Tennessee, you go from basically from the Kentucky state line to the Alabama state line, and from the Tennessee River in the west over to the Cumberland Plateau in the east. And that is the area that we issue forecasts and warnings for. Now, we're going to start off with radar. Radar actually is an acronym that stands for radio detection and ranging. And there's again a map with all the Doppler weather radars, and including ours. And there's the good thing about the Doppler radars is that they're all kind of hooked in together, sort of like a computer network, so we can use multiple radars, not just our own. Sometimes we'll use the Doppler radar up at Hopkinsville, Fort Campbell, or the one down at Huntsville, Alabama. Those both cover a good chunk of our county warning area. So technically, even if our radar might be down, and sometimes it is down either because of a technical issue or just for general maintenance, there's other radars we can use to interrogate storms here in Middle Tennessee, and not just our own. Most of these were installed during the 1990s. Ours was installed in 1994. And there are currently 159 of those things around the country. There are, it's not a perfect system, obviously. Nothing is. It does have its limitations just due to the laws of physics. The radar has poor resolution at farther distances, just because the radar beam spreads out the farther it goes. And so we don't get storms that are at great distances aren't resolved as quite as cleanly as ones that are close in. Full radar scans take from 4 to 10 minutes to do, because we don't just take one scan. We'll take scans at multiple levels in the atmosphere to give us a 3D view of each storm. And so it takes a few minutes to do that. Obviously, during severe weather, we'll go with a faster scan strategy, so it'll be closer to 4 minutes. And then on a day or night when there's no weather going on, we'll just do a real slow scan, kind of go easy on the radar, and do what we call clear air mode. It takes 10 minutes to go through that. We can miss some brief tornadoes and severe weather, like pulse type storms that pop up in just a few minutes. Sometimes if that happens between scans, we'll miss something, or a weak tornado that spins up, especially it's not real deep. Sometimes they can happen underneath the radar beam and we don't see it. So it does have its limitations. Here's a graphic to show that the farther out the radar beam gets, the higher above the ground it goes. And that's not just Doppler radar, that's any radar. That's just the physical properties of electromagnetic radiation. They don't curve quite as sharply as the Earth's surface. And so the farther away the beam gets from the radar, the higher up it goes. And so, a storm that's happening over Nashville, just a few miles from the radar site, we can sample very well. But if you go to, say, a place like Salina, which is, 50 or 60 miles from the radar site, by the time the radar beam gets there, it's a mile above the ground. So anything that happens underneath that 5,300 feet, we won't see with our radar. So that's where multiple radars come into play, where we can sample storms better using multiple radars rather than just our own. Spotters, which is you all, provide critical details on what's happening at ground level. Again, because we see storms and we don't really see them. We just see them graphically. You see them in person. And we see with the radar only what's going on above the ground. Spotters tell us what's going on at the ground where the radar beam doesn't sample. And so that's why, even despite our wonderful technology, we still rely on spotters to give us ground truth reports of storms that we're warning on or thinking about warning on. So that's why we train spotters as we do. Now, when you think of Tornado Alley, you probably Hopefully that did the trick there. I'm still learning about this thing. Again, I do this twice a year, and does that look good, everyone? Somebody come back and just let me know if that clears everything up. Thank you, Russell. Appreciate it. Appreciate that. Okay. Now, hopefully, I've got everything on track. Okay. When you hear Tornado Alley, you probably think, well, Great Plains, Texas, Oklahoma, Kansas, that area, which is traditionally has been Tornado Alley, and it's still the place where we get a lot of higher percentage of large tornadoes. And by large, I'm talking the F4s and F5s than we get here in Middle Tennessee. So that has traditionally been Tornado Alley, the Great Plains. However, nope, that's not what I'm looking for there. There we go. Now, the real Tornado Alley, and we're using statistics, annual kilometers of tornado path within 25 miles of a point, technically is how this is figured. But when you consider all tornadoes, not just the large ones, the real Tornado Alley is a lot closer to home. And there's a bullseye there over northern Alabama and central Mississippi, where they have the highest percentage of annual kilometers of tornado path within 25 miles of a point. And Killer Tornado Alley similarly is a lot closer to home than we would like it to be. And this is the relative frequency of killer tornado events over a 50+ year long period. This was a study done several years ago, and it shows that the frequency of killer tornadoes occurs over the Mid-South, northern Mississippi, northwest Alabama, west Tennessee, and whatnot. And so whereas traditional Tornado Alley is where it's always been, Killer Tornado Alley is much closer to Middle Tennessee, where we have a higher percentage of killer tornadoes. Now, when we go through our tornado climatology, and this is this is based on, I think we have over 600 tornadoes in there, maybe 700 now. Anyway, every tornado that we've been able to catalog that has occurred in Middle Tennessee, going back to the 1800s even. So we have a pretty good database of tornadoes. Our tornado season, not to anyone's surprise, occurs during the months of March, April, and May, when we get almost 2/3 of all our tornadoes occur just during that 3-month span. And then there's a significant drop-off that actually begins in late May. After, I forget what the date is, but after something like May the 18th or May 20th, we really start to see a significant drop-off in tornado activity. So the summer and winter months generally have the lowest frequency of tornado occurrence. However, there is a secondary spike that occurs during the month of November. We have had just within the last 15 years or so, about 2 or 3 significant November tornado outbreaks, which have kind of pushed that number upwards. That's why in November we'll have a secondary severe weather season awareness just for a day, just to let people know, hey, we can still get tornadoes this time of year. We're not totally safe, but again, we're now in tornado season, which is why we conduct the spotter classes this time of year, to get everyone prepared for the upcoming severe weather season. Now, when we further break tornadoes down by hour of day in which they occur, you will see that the hours during peak daytime heating and just after are the most frequent for tornadoes to occur. Mainly, through the middle afternoon to the early evening is when tornadoes occur more often than not. And then once we get to the late evening and overnight, and then especially the early morning around sunrise, there's a real drop off in tornado frequency, and it's all heat driven. Obviously, the hottest time of day is going to be most conducive for tornadoes, and the coolest part of the day is going to be least conducive. Kind of makes sense there when you think about it. Now, when we break our tornadoes down into weak, strong, and violent, EF0 to EF1 being weak, EF2 to EF3 being strong, EF4, EF5 being violent, we'll find that fortunately, most of our tornadoes, 61%, fall into the EF0, EF1 category. And it's very rare to get a tornado fatality with a weak tornado, as you could imagine. Even though strong tornadoes, EF2, EF3, make up just over 1/3 of all our tornadoes, more than half of all tornado fatalities occur with those storms. And then when you get to the violent storms, the EF4s and EF5s, and I think there's only been about 22 or 23 of those in our entire database, they account for a disproportionate share of our tornado fatalities, 44% in fact. So as you would expect, the violent tornadoes do tend to be the most deadly. Okay, we're not going to spend a lot of time on the periodic table of all our products that we issue. We issue a lot of products, ranging from routine products like the zone forecast product that goes on the weather radio, to the forecast discussions, to the fire weather forecast, and then there's a whole smorgasbord of statements and warnings and watches and advisories as they relate to severe storms and winter weather and whatnot, and flooding. And so there's a lot of products that we issue. Some we don't ever issue at this office, like the volcanic eruption thing. We don't have to worry about those because we don't have volcanoes here. So there's, and blizzard warnings, which I've been here 23 years, and we've never had a blizzard since I've been here. So some we don't issue, some we issue very frequently, but just let it be known there are many weather-related products that we issue here at the Weather Service. One of which is what we call the Significant Weather Advisory. This is something that we started doing just a few years ago it's not a warning. It's not the same as a warning. It's not meant to be a warning. It's just an advisory in the event of a sub-severe thunderstorm, which can still be hazardous. For example, if there's a lot of electrical activity, we don't issue severe thunderstorm warnings for lightning, even frequent lightning, but we'll let the significant weather advisory cover that. And sometimes you can get wind gust in a thunderstorm that is not severe, but still could push over a weak tree or a shallow rooted tree or a tree that's been kind of loosened up by wet ground or whatnot, and small hail as well, which can do damage. Even hail under an inch can do damage. And rotation, if we see some rotation in a storm, but it's not strong enough to warrant a tornado warning, we can mention that in there too, that we're watching for rotation. Now, up from that is the severe thunderstorm warning, and there are technically two things we used to define a severe thunderstorm warning: wind gust of 58 miles per hour or greater. And you say, why 58 miles per hour? 58 miles per hour is 50 knots, and weather, we typically operate in knots, which is a nautical mile per hour, but in everyday lingo, it's miles per hour. So we convert that to miles per hour. So that's why the 58 miles per hour. And or hail 1 inch diameter or greater meets the criteria for a severe thunderstorm. Or a tornado, but then for a tornado, we would issue a tornado warning. So that's a different animal right there. So when we issue a tornado warning, it means that a tornado is likely to develop, or is already occurring. And there are several sources that we use to determine whether or not to issue a tornado warning, one of which is the radar indicated tornado. And the graphic that you're seeing now is what a tornado would look like on radar. On the left is a reflectivity image, which is typically what you'll see like on TV or whatnot. They'll show reflectivity, which just shows where a storm is and how intense it is. And on the right is a velocity product. Technically, it's called storm relative motion, the SRM product. And that white circle you see is encircling, we call an inbound outbound couplet, where the radar site is actually up to the north of that couplet, and the green that you see is wind moving very rapidly toward the radar, and the red is wind moving rapidly away from the radar. And when you see them juxtaposed like that together, that's called gate-to-gate shear, which indicates anticyclonic rotation, which is what the signature is given off by a tornado. So in this case, the radar would have given us enough evidence to issue a tornado warning. Sometimes radar can pick up a debris signature, which is very distinct, where the tornado picks up, debris like, parts of, houses, or, parts of trees, or, other, whatever it picks up off the ground, and lifts it into the air. It gives off a very distinct radar signature, because, the radar sees those as targets and sends it back to the radar, says, hey, I'm seeing, or sends it back to the radar site, says, hey, I'm seeing something here. And it looks a lot different than, normal precipitation echoes. And so if we pick up a debris signature, we can, in the body of a tornado warning, we can say, this tornado is confirmed by radar. It is on the ground. Even without a spotter report, we can use a debris signature to confirm a tornado. And we have different wording within our warning products to convey the damage threat. For example, on the left, we use the debris signature to warn the public that a confirmed large and extremely dangerous tornado was located 8 miles north of Hohenwald, moving northeast to 70 miles an hour. And on the right is a similar warning, except if you look at the very top line, we declared or not we, this would have been the Memphis office, because they cover that part of northern Mississippi. Tornado emergency for Holly Springs, which is a town just southeast of Memphis. And so that would have been in the event of a violent tornado. And so they use the tornado emergency to convey the threat and hopefully, get people to take it seriously and take shelter. So flood advisories, this is something that we've done a lot of lately with all the rainfall we had in February and all the flood products that we had to issue. As a result, we'll issue a flood advisory for generally minor flooding or localized flooding, such as minor ponding on roadways that typically occurs during and right after a downpour, that typically goes away after the rain stops and whatnot and drains out, or rises on small creeks, streams, or rivers that tend to be kind of flashy. We'll issue flood advisories for those. And then up from that is the flash flood warning, which is a bit more serious than a flood advisory. And we'll issue those for heavy rainfall, typically from thunderstorms, that results in significant flooding of roadways, such as road closures, or water rescues. If water rescues are underway, that would be something that would necessitate a flash flood warning if one weren't already in effect. cars stalling in floodwaters, which does happen sometimes, especially in poorly drained areas, and flooding of businesses and homes. Those are things that would necessitate the issuance of a flash flood warning. So what is a watch versus a warning? A watch, and by convective watch, we're talking either severe thunderstorm watch or tornado watch. A convective watch is issued not by the local office, but by the Storm Prediction Center. And a watch will typically cover many counties, or often it's parts of more than one, all are part of more than one state. And so these are a lot of times coordinated between the SPC and multiple field offices like us in Louisville and Memphis and Huntsville and whatnot, if it's going to cover, affect our areas. And a severe thunderstorm watch means severe storms are possible. Ideally, they would be issued before the onset of any severe storms, ideally. And so it's just to kind of heighten public awareness, to be prepared that severe storms are possible, that weather conditions are favorable for storms, for severe storms. And then a warning. Warnings are all issued by local offices, and they cover a much smaller area than a watch. A portion of a county, or portions of 2 or 3 counties. And that they convey the threat that severe storms are expected, that large hail and or damaging wind is occurring or will shortly occur at this particular location on the map. And so and also severe thunderstorm watch is typically several hours in duration. A severe thunderstorm or tornado warning will typically run on average 30 to 45 minutes, sometimes shorter, maybe longer, but we try to not to make them go for too long. So they're a lot more short fused than a convective watch. Now, with technology the way it is, fortunately, there are many ways that you can receive warnings. 2 of the more traditional methods are NOAA weather radio and your local TV and radio stations. However, the technology has enabled us to get out warnings via cell phones, and if you have your WEA set up on your smartphone, you can get warnings. I think it's tornado warnings and flash flood warnings right on your. I mean, it just pops up right on your phone. You don't even need an app for it. It just happens when they're issued. And so you can set that up in your phone if you haven't already to receive those. And also, our warning products are automatically go out via Facebook and Twitter as well, just within seconds. The timing on those is really good. We get those out fast using social media. So there are many ways nowadays to get to receive your warnings from the Weather Service. Now, those WEAs, or wireless emergency alerts, a little bit more about those. The ones that, again, affect us here in Middle Tennessee are the tornado warnings and the flash flood warnings. And again, these are sent through mobile carriers. There is a 90-character max, so you can see the sample alert on the right. It's very short. I mean, there's not a whole lot of information with it. So if you wanted more information, you have to go, pull up the body of the warning, or go, wherever you go to get, the full text of the warning. But it is there just to warn you that the area you're in would be under a warning until such and such time. So those are useful. And then there's NOAA weather radio, which we still tout as the fastest way to get your warnings. It's just the process is fully automated, and it takes literally just seconds from the time we transmit the warning until it's tone alerted on NOAA weather radio. And again, weather radio operates 24/7, and they're programmable now, so you can program to receive just warnings for your county or multiple counties if you choose. They're available in many places. And so it's always good to have more than one way to get your warnings, instead of just having one method. A few safety rules, tornado safety rules. These are just conventional wisdom things that we've been telling people for years, best practices, kind of trial and error, the things that work versus things that don't work. It's always best to seek shelter in a basement. If a basement is unavailable, like I don't have a basement, and so we'd have to go to the bottom floor of our home, an interior room like the coat closet, some room that where there's no windows around you. We tell people to put as many walls between you and the outside as possible. And of course, if you're in a public building or an office building or a department store or a movie theater or whatever, they all have, designated shelters available. So go there. And if you're in open country, find the nearest available shelter. Not a good place to be, though. You can see this is a two-story home that was hit by a tornado. And I'm not sure what the F scale classification was. I would guess F2 or above. F2, maybe F3. And you can see the second story is almost totally obliterated, but the bottom floor is largely intact. So you would have been much safer on the lowest floor, obviously, than if you'd been on the second floor. And then, not to pick on people with mobile homes, but a mobile home is not a good place to be in a tornado. This is an example of a mobile home that was struck by an EF2 tornado, and as you can see, there's nothing left of the mobile home except debris. And so mobile homes are easily damaged and destroyed by tornadoes, much easier than a frame home. They can be very easily overturned. Even straight line thunderstorm winds could do significant damage to a mobile home. If possible, abandon mobile homes for a community shelter or sturdier building if available. And then on the right, just by comparison, you can see the EF2 damage to a larger frame home, where again the upper floor is obviously a mess, but the lowest floor was not undamaged but left mostly intact. This tornado in question then continued into Cook County, still at EF3 strength. This may be a different tornado, actually. It was an EF3. And this is just a post-storm write-up from one of our offices. Still at EF3 strength, it swept about 35 manufactured homes into a pile of rubble at the far end of this mobile home park. 7 people were killed. And then it went on after that. That was a mobile home park that was struck by an EF3, where 7 people unfortunately were killed. So that's what that kind of damage looks like. Automobiles are not safe in tornadoes. I know the tendency is to attempt to outrun a tornado, but we urge people not to do that. Instead, it would be better to abandon cars and trucks for a storm shelter or a sturdy building if possible. If not possible, just get down in your car and cover up, or maybe even seek shelter in a low-lying ditch where you're not completely safe, but you're safer and less exposed than you would be in a car. Now, damaging wind safety rules. We do have our share of those as well, and damaging winds are what they are. They can be dangerous too. For example, a man was killed just here in Rutherford County when a tree fell on him during a thunderstorm. Storm passed through the area during the late afternoon, bringing with it reports of hail and strong winds. According to the fire chief, a 64-year-old man was riding an ATV toward his house when a large hickory tree fell on top of him and killed him. And so, again, during a severe thunderstorm, please take shelter inside, preferably away from glass. If caught outdoors, stay away from trees and power lines. Anything you can remove yourself from anything that might blow over. You're better off. Large hail safety rules. Again, please take shelter inside. As you can see, this poor gentleman on the left, hail can do damage to your body if you're caught outside. And I'm sure that must have been quite painful to be hit by hail like he was. That was the result of quarter to ping pong hail, which is kind of rare here in Middle Tennessee, but it's not unprecedented. We'll get that happen a few times. Quarter to ping pong size hail and a few of our, especially during the spring. So it's not unheard of to get that kind of hail here in Middle Tennessee. So obviously take shelter inside a building away from glass, and if you're in a vehicle, stay there and wait for the hail to end. Lightning safety rules. People do get struck by lightning, but it's rare, but it does occur. Obviously, go indoors during an electrical storm, inside a building or an automobile. You're safe in an automobile during a lightning storm. Stay away from all wired electronics and plumbing, because lightning obviously is electricity, and electricity loves wires and water. Very good conductors of electricity. So stay away from those things. Lightning fatalities in the United States, there are on the average 2 to 4 dozen of those per year that occur in the United States. So they are relatively rare, but it does happen. Lightning fatalities. Oops, I missed the question. I didn't put the question on here. Sorry about that. Flash flood poll. I wonder what that was. Well, sorry about that. There's no poll question, even though the slide said poll question. Flash flooding, believe it or not, is the #1 weather-related killer in the United States. Not tornadoes and not winter weather, not the heat, not the cold, but flash flooding. More people die from flash flooding than any other weather-related phenomenon. And just in 2015, for example, and you could say this for just about every year, most flash flood fatalities occur in vehicles, most of which occur when somebody tries to drive their vehicle into water. And that's why we came up with the slogan, turn around, don't drown. And it sounds kind of corny, but there is an element of truth to it, because there are people who get killed when they try to drive through water that's moving swiftly, and the cars get swept away, and one thing leads to another. So that's our primary flash flood safety rule. 12 inches of fast moving water can carry away a small car. 18 to 24 inches of fast moving water can carry away most large SUVs, vans, and trucks. Moving water is very powerful. Sometimes we don't realize how powerful it is, but it does, has quite a bit of force to it. Thunderstorm basics, kind of shift gears for a little bit and talk about just the kind of the meteorology behind and related to thunderstorms. The worst kind of thunderstorm is the supercell thunderstorm. And we don't get many supercells here in Middle Tennessee. We do get some. Your bigger supercells are going to occur out in the Great Plains, but it is the strongest and longest lasting type of thunderstorm. Supercells all have this in common. They contain a rotating updraft called a mesocyclone. There is a high severe potential with supercells, and not just tornado potential, but also the threat of wind damage and hail. And in fact, the updrafts in supercells are so strong that they can produce a very large hail and also the most violent tornadoes. Most of your, in fact, if not all of your large violent tornadoes are the result of supercell thunderstorms. They typically, most often, move from southwest to northeast in Middle Tennessee. Their typical movement is southwest to northeast. That's important when we talk about spotter positioning, to know that's the typical movement. Just looking at a schematic of a supercell from the side, there's all the different parts to it. You've got the updraft and the downdraft portions of the supercell. The updraft portion, underneath the updraft portion, is where you would find the wall cloud and any tornado that might form. The downdraft section is where you would have the the strong outflow, the straight line winds, and your rain and or hail shaft would be underneath the downdraft. And then up on top, there's something called an anvil, which is where the top of the supercell takes on a flattened appearance. And that occurs as the rising air comes in contact with what's called the tropopause. The tropopause is the boundary between the troposphere, which is the lowest level of the atmosphere, and the stratosphere. And because the air in the stratosphere warms up due to the ozone layer, it sort of acts as a barrier that most updrafts kind of hit that barrier and just stop. And so that's why the top of a supercell will kind of take on a flattened appearance called the anvil. However, during a very strong updraft, the updraft can actually punch through the tropopause into the stratosphere, and we call that an overshooting top. And that's, if you look at the top of this schematic, that's what that is. So if you see, it looks kind of like cauliflower. So if you were looking at a supercell from the side and saw that, you would immediately know that, wow, that storm's got an overshooting top. So it must have a very strong updraft and an increased tornado potential as a result. And there's just a photograph, a side view from a supercell, and you can't really see the flat anvil light. You can see the anvil underneath as the those clouds on top kind of spread out right underneath the tropopause. But you can still can't really see any overshooting top either, because it's not far enough away. But you can see where the updraft is just by the vertical growth in that supercell thunderstorm. And then you can see there the updraft on the right of the storm. And if I had to guess, I don't know this for a fact, but just judging by the way the storm is excuse me, angled, and assuming that it's moving from southwest to northeast, I would say that we're on the north side of the storm looking toward the south. And so you can see the updraft there, which is usually located in the southwest portion of a supercell, which is rain free. You can see just right underneath that updraft, there's no rain there. And then right below that blue arrow, you can see the rain shaft there. That's where the downdraft is going to be, where you can see that real heavy torrential looking rain. That's where your rain shaft is. Maybe a microburst, strong outflow, whatnot. So that's the supercell from the side there. So you've heard mention, I'm sure by now, this curious feature called a wall cloud. A wall cloud is just a lowered cloud base beneath an updraft, and it appears due to lower pressure, which causes condensation. And think of the updraft portion of a supercell as sort of like a partial vacuum. Um, um, the updraft sort of operates as a vacuum where air is removed from the updraft and it's not replaced as quickly as it's removed from the updraft portion of a supercell. So there's a partial vacuum there where the air pressure is lower than in the surrounding part of the storm and the surrounding atmosphere. Wall clouds will typically slope upward and into the updraft, and tornadoes typically drop from wall clouds. No, not in every instance, but and not every wall cloud produces a tornado, but with very rare exception, every tornado that occurs, at least in a supercell, will drop from a wall cloud. That's going to, in a later slide, that's going to be your action area. We're going to talk about action areas, and that's the wall cloud is the action area. Oh, there it is right there, the action area. You can see the rain-free portion of the supercell to the left. That's where your downdraft is. The rain-free portion is where the updraft is occurring. And you can just kind of see there a partial lowering, right? Just look through the barbed wire fence there. You can see a partial lowering of the cloud. That's not a fully developed wall cloud yet, but it sure looks suspicious, like it might develop into a wall cloud. And one problem with using still photographs is that we can't tell for sure whether or not there's rotation in the wall cloud, as a video would show. So we'll just assume that there is there. Now, again, wall cloud does not always mean tornado. Not every wall cloud produces a tornado, but certainly if one's going to occur, it's going to occur underneath the wall cloud. So that's the area that we're interested in most. So when you're spotting a supercell, if you're in that position, the things you want to look for are rotation, persistence. Is it been rotating for a while? And do you see any rising motion? Because there will be kind of rising and falling motion during various parts of that action area. And so you want to see if there's any kind of rising motion up into the cloud or not. All those would be indicators of an increased tornado threat. Hang on just a second here. Will a tornado always form in the rain-free updraft, downdraft area? In a supercell, yes. Now, again, most of our tornadoes don't form in supercells. We get to that a little bit later on. But in the with a supercell, for all intents and purposes, yes, tornadoes are going to form in the rain-free updraft area. And the reason is because if you look in the rain shaft where the downdraft occurs, the updraft has been cut off there. There's no updraft. And for a tornado to occur, you need an updraft. And so that's the part we're looking at. So it's a good question there, Christian. Thank you. Now, another feature, and this is not just indicative of supercells, these can occur with really any thunderstorm, is something called a shelf cloud, which is an indicator of strong winds. They appear, and we see these fairly frequently in Middle Tennessee. We'll when we're working severe weather, just following along on social media, we'll get, sometimes people will snap us a photograph of a shelf cloud, and so we do get these fairly frequently in Middle Tennessee. They appear sort of a wedge-shaped cloud. They occur on the leading edge of a gust front. They slope downward and away from the rain-hail shaft, and they again can occur with any type of thunderstorm. They also occupy a large expanse of horizon. These are not small clouds. They can can stretch out from left to right for a good area, and they have a very distinct look to them. So you'll know it when you see it. A shelf cloud. It's just an indicator of potentially strong winds right behind the shelf cloud. Again, the difference between shelf clouds and wall clouds. Shelf clouds slope downward and away from the downdraft. The wall cloud slopes upward and into the updraft. There's a significant difference there. Funnel clouds typically form from a rotating wall cloud. Always watch for debris at the surface because just because the funnel isn't fully filled in doesn't mean it's not touching the ground. Watch to look for debris at the surface, especially the one on the right. You can see the funnel cloud forming a very distinct V beneath the wall cloud. And if you follow it down to the ground, it looks like it hasn't reached the ground until you get to the ground and you see there's debris directly below the funnel cloud. And so that's actually not a funnel cloud, that's a tornado that just hasn't, the condensation funnel hasn't yet completely filled in. So always follow it down and look for debris at the surface. That's a telltale sign of whether or not the funnel clouds actually reach the ground or not. And so there's if you're on the right, I'm sorry, the storm on the left looks like a funnel cloud only, not a tornado. Although there's some vegetation there kind of blocking the view of the ground. But from what we can see, there's no debris being generated at the surface. So that's probably just a funnel cloud on the left there. Now, tornado has a very has a very specific definition, and it is this. It's a violently rotating column of air in contact with the ground and extending from the base of a thunderstorm. So when we use the word tornado, it already we often hear the phrase tornado on the ground, and there's nothing wrong with that. It's just kind of redundant because a tornado is, by definition, on the ground already. And so that's the funnel cloud is not touching the ground. The tornado, by definition, is a violently rotating column of air in contact with the ground and extending from the base of a thunderstorm. And tornadoes are not always classic looking or well defined. The one on the left kind of sort of has a bit of a jagged appearance. It's not really smooth, although it is definitely a tornado. There's no question about it. Whereas the one on the right is a tornado that appears to have reached its what we call the rope-like stage, which is near the end of the life cycle of a tornado, and we call it the rope-like stage because it looks like a rope. But if you kind of follow the tornado down to the ground, you can see right behind one of the telephone poles there where it is still kicking up debris at the surface. So it's still a tornado, even though it looks small. It's still still producing debris at the surface. Now, there are tornado lookalikes that to the untrained eye, and we do get lots of reports of these that people that aren't trained spotters see and think, tornado, just because it looks kind of ominous like a funnel. One of those is scud clouds, which are literally just cloud fragments, for lack of a better term. The exact terminology is cumulus fractus. The Latin word fractus kind of means, I think fragments. So that's what a scud cloud is. They're ominous looking but harmless clouds that occur beneath the base of a thunderstorm. They can occur with the updraft or the downdraft, and if you watch them closely enough, you will see no rotation, no rapid vertical motion, no inflow. They're just harmless, but they can look ominous. So that's one of the reasons why we bring this up during spotter training, is to teach you to differentiate between harmless looking scud clouds and an actual wall cloud or funnel cloud or tornado. Night spotting is dangerous for obvious reasons. It's hard to see. And so we ask people, don't put yourself in harm's way. Don't actively pursue storms at night. And also be honest in your report. Usually night spotting, the only time you might see a tornado is during a lightning flash, when you get just a fraction of a second view, and you don't get a real close look at it. And like this photograph that's been, I assume, illuminated by a lightning flash. It looks ominous. That's probably just scud there, but you don't get a long look at it in real time. It just an instantaneous flash. So just be very careful at night, both in your safety. Don't pursue these things, but in also your reporting. Be honest in your reports about what you're seeing, and just realize the limitations of nighttime spotting. So what is this? What do you see here? But there's a couple of very distinct features that we're looking for. And number one, do you see a wall cloud? And I would have to say there is a very distinct wall cloud in this photograph. And again, I know it's a still photograph. We can't tell what kind of motion it is. We can't tell if there's any rotation or not. We'll just assume there is. Do we see what looks like a funnel beneath the wall cloud? And there is a funnel. You can see beneath the wall cloud. And the next question is it a tornado or is it just a funnel cloud? And if you follow it down to the ground, you can see debris being picked up at the surface. And so it is a tornado. So that's the things that we're looking for there. The wall cloud, the funnel cloud, and in the absence of a fully developed condensation funnel, is there debris at the surface? Yes, there is. Okay, what is this feature? Is it a wall cloud? To me, it looks like a wall cloud. And even though we have a still photograph, you can kind of see that there is some how the cloud is kind of in the foreground, is kind of wrapped. So there looks like there's at least a mesocyclone here, and that probably is a wall cloud. What is this feature? It is a shelf cloud. Very good. Whoever said that, I think we probably had multiple people there, but yes, this is a classic shelf cloud, indicating not necessarily a tornado presence that may be farther back in the storm. Doesn't mean there's not one, but this indicates a very strong downdraft of wind coming out from beneath a thunderstorm. What is this feature? This is this is scud. Very good. A couple people said scud. This is a scud cloud. Very good. Harmless scud. Okay. What features can we identify? Very similar to the one we saw a few slides ago. You can definitely identify the wall cloud. This may actually be the same storm, just a different frame taken a little while later. Wall cloud, definitely. Is there a funnel? Yes. Is there a fully developed condensation funnel? Not yet, but there is a debris at the surface, so we can kind of fill in all the blanks there and call this a tornado producing supercell. Okay, well, we got it. Okay, good deal. Spotter positioning. We talked about spotter positioning just briefly a few slides ago. It's important, obviously, to be in the right place when you're trying to spot. And sometimes you're not going to be in the right place. And please do not put yourself in harm's way trying to get to the right place. Because most supercells move from southwest to northeast, and because the updraft slash wall cloud slash tornado typically occurs in the southwest portion of the supercell, you typically want to be south of the supercell to be able to see the tornado. And I'll show you what I mean here. This is a radar detected supercell tornado, a supercell thunderstorm with an obvious tornado. So if you're at point A, you're not in a good place, because if you're trying to spot a tornado, you're going to be looking through a lot of rain and maybe some hail, and you're not going to see the tornado from that position. If you're in at point B, you're not in a good place. You'll have a very good view of the tornado, too good a view, in fact, because it's headed right for you and you don't want to be there. So position C is the best place to be, because you've got a clear view of the tornado and it's not heading toward you. So the idea is to spot safely. And so of the three options, C is obviously the best option for successfully spotting a tornado safely. Again, the action area, that's the position of the wall cloud, funnel cloud, or tornado. And you can see the pink and purplish colors there. That's where the strongest radar echoes are being detected. That's where your heaviest rain and probably hail, the hail shaft, is going to be located. Not a safe place to be. Also, you're not going to see the tornado from there either, because it's going to be blocked out by rain and hail. So if you're north of the storm, you're generally safe, but you're not going to see anything other than rain. And that's what it will look like. So you're not going to see the tornado there. If you're east of the storm, you might see the tornado, and you might see it coming right at you. So you don't want to be there either. So obviously southeast or south is the best place to be, because you're in a rain-free area and you can see the tornado and it's not coming at you. It's a safe place to be, and you are successfully spotting a tornado. Also, keep in mind that even though we talked about supercells typically moving from southwest to northeast, they don't always move in a straight line. And these are the results of one such tornado survey that was conducted, and I'm not sure where. It's El Reno. I'm not even sure where that is. It's not here, that's for sure. Looks like out in the Great Plains, given that the roads are so straight. They're not that straight here in Middle Tennessee. So anyway, they don't always follow a straight line, and so just be aware that one moment you may not be in its path, and the next moment you might, if it turns, and they do turn a little bit, even though the general motion is from southwest to northeast. So how do you report severe weather to the National Weather Service? There are ways to do it. Here are the things we need to know at the Weather Service. We need to know what, when, and where. Specifically, what type of severe weather is occurring. Do you have hail? Are you seeing a wall cloud? Did you get wind damage? When did it occur? Is it occurring now? Did it occur 5 minutes ago, 10 minutes ago, 15 minutes ago? Where is it? Are you, a lot of times we'll get a report. Somebody will say, I'm located at the corner of Edgefield Road and Poplar Drive, and I have no idea where that is. You could be anywhere. So a better report would be, I'm located in Erin, Tennessee, or I'm located 5 miles north of Gallatin, or I'm located on Highway 231, about 8 miles south of Lebanon. Those that tells us a lot more than an intersection, because we don't know where every road is in Middle Tennessee, because there's a lot of them. Be clear with your location. If we kind of dig down deep enough, we can take an intersection, but we kind of need to know a city, because we can use Google Maps to find it. Say I'm in Hermitage, located on Couchville Pike, half-mile east of the intersection of Weekly Lane. Great, we know where the city is. Don't just assume we know what city you're in just by giving us street names. There are trees down on power lines and on the road. Great report right there. Very to the point, tell us exactly what we needed to know. And we can often use, if you don't know what time it occurred, like if you come across damage after the fact, we can use radar data to see exactly when the wind maximum or the hail core hit your area. We can use radar to time it, to figure out what the time was that it occurred. So we need reports of flooding, hail, even non-severe hail, even like half-inch hail or 3/4 inch hail, ice and snow. How deep is it? High winds and wind damage, funnel clouds and tornadoes, obviously. When you report hail, we ask that you compare it to a common object like a coin. Coins are great. We love coins. Penny, nickel, quarter, $50, or golf ball, or when you really get into the large hail, baseball. And we actually have had hail as large as softball here in Middle Tennessee, although it is extremely rare. It has occurred, but typically we're usually golf ball or smaller. And also nowadays we get a lot of pictures via social media. And these are great as long as we have something to compare it to, like the one on the left. That looks like a large hail, but we don't know if that could be a child's hand, or we don't know how big the hand is. Lay it next to something like a coin, the one on the right, that tells exactly what we need to know. That's probably quarter size hail is 1 inch hail, so that larger hailstones probably close to 2 inches in diameter. So that gives us a lot better estimate there of the hail size. Wind damage and estimates. Wind damage is just important as wind speed measurements. A lot of people nowadays, not everybody, but several people have home weather stations with anemometers, so you can actually measure the wind speed or wind gust. Just know that if you give us a wind estimate, most estimates are too high. People typically get excitable during a severe storm and tend to overestimate the wind speed. So what might be reported as a 60-mile-an-hour wind might really just be 40 miles per hour, which is the difference between severe and non-severe. So just try to be realistic about your estimates. Flash flooding, we need to know about that as well. Snowfall accumulations, measure on a hard, flat surface, not grass, for an accurate measurement, like your driveway or your deck, or even the hood of a car. Something hard, a hard surface, gives us accurate snowfall measurements. And then how to report. If you can call our 1-800-SPOTTER line. 1-800-267-8144 is our 1-800-SPOTTER line. You can also report to us via Facebook or Twitter. And during a big event, during a severe weather event, We'll have, obviously we have extra staffing during a big event like that. Even a winter weather event will have extra staffing just because of the workload. And so we'll have a person dedicated just to social media, just to go through all the Facebook reports and, and Twitter's tweets, looking for reports of severe weather or snow or whatever the event happens to be. A good Facebook report would be like this. As you can see at the top of the post is a solicitation for reports. And then there's a report there, very short, but it gives us all the information we need. Between 3:20 and 3:40 p.m., wind gusts of 60+ miles per hour in Adams, Tennessee. We got when, we got what, and we got where. That's perfect. And then on Twitter as well, we ask if you can remember when tweeting storm reports to use the T-Spotter hashtag, because we'll go into the Hoot feed, which is part of Hootsuite, which we use here. And so a Hoot feed lets us, you can type in the T-Spotter hashtag and just follow everything that comes across with that hashtag. And if we could get at least most people using the T-Spotter hashtag, that really helps us kind of funnel the storm reports into one feed, makes it real easy to find them. Please help us and use T-Spotter. And ahead of a big event, we'll send out reminders. Hey, please don't forget to use T-Spotter when sending us reports. And that concludes our class. I appreciate your attendance tonight. These are always fun to do because nobody has to travel anywhere. You can sit there and I can sit here and we can tell you most everything that we would have told you in person. So that's my email address. If you have any questions at all after the fact, something you think of or something we might have missed, something that wasn't clear, just shoot me an email at mark.a.rose@noaa.gov and I will do my best to answer. And then if you want a certificate that you completed this class, you can go to that URL above at weather.gov. There's a PDF there that has our logo and everything in it, and all you have to do is fill in your name and you can print it out and hang it up and impress people with it that you completed the basic spotter training from the National Weather Service. So I'll leave that up for a moment to copy that down. If you want your own spotter certificate, you are welcome to go get it and put your name on it and whatnot. But anyway, that's my email address. Again, mark.a.rose@noaa.gov. And if no further questions, we will go ahead and terminate the presentation. And y'all take care and have a good night.